Saturday, and Sachin mentioned that he would not be able to join, but that's fine. So I'll record the meeting and then put it up. You can have a look at the meeting and then ask questions on either Monday if you get a chance, or if you don't get a chance, Tuesday or Wednesday, right? So that's totally fine. Feel free to interrupt me with questions, right? So again, more questions you ask, the interesting the class is. So we were looking at, so getting back to where we were looking at why F star, right? And then we said, okay, F star is used in a lot of places, including the main motivation is to build a um, verified version of the internet security stack, right? Which is essentially HTTPS. And the products of this are all in different projects, including Chrome. So Chrome is missing from here. So Quick Protocol in Chrome is actually using an artifact from the FStar project. All of this is open source, right? One of the things that has really changed in the recent, say, maybe 5 years, I wouldn't probably extend it beyond 5 years, is that all of the companies are incredibly behind open source, and the biggest contributor. So can you, let's take a guess, right? Who do you think is the biggest in terms of companies? Who do you think is the biggest contributor to open source software on GitHub? Any thoughts? Good guess. So Sriram has Google, but that's not right.
I think it has to be Microsoft.
Yeah, it is Microsoft. So surprisingly, right? So we've always associated Microsoft with closed source software and such, but they have incredible open source contribution these days, including the Zepstar project, right? It's completely open source. All of the so by open source, it's not just like oh, building an artifact and then throwing it out there. All the development discussions and everything happens in the GitHub discussions, right? You can actually see how the software is constructed. Of course, there will be closed room meetings, but most of it is open source, and an excellent development. Um, if you want to see how good projects are to be developed, um, Linux kernel is not the right one, right? So they have some really big people with huge egos, right? It works out well, but that's not a really good project. Look at Rust, right? So Rust is completely driven by this very nice mechanism that is completely open source. Everything is done on GitHub. They have this nice RFC process. You can just go ahead and say, okay, here is a feature that I want. Here is how I plan to. Here is what you will get, right? And then you can request for a comment, and then obviously you also have to have like a sane idea and so on, but the process is open, which is incredible. So all of the things that we discuss here are open. You can play around with any of these projects. Coq is also open source, right? All of these are there for you to explore. Go ahead and explore, right? I wouldn't want you to say, okay, you should explore this or that. If you really want to improve, just pick up some project that you find interested. It can be anything at all. It doesn't have to be PL related, but open source movement is alive and kicking, and I really recommend you to just be even if you don't contribute. The contribution is not just code, right? You might just go and improve the documentation, for example. That is also a good contribution. So get as you grow as software engineers, perhaps you might not have the opportunity to work on open source project in your uh, at your employer, right? But if you have interest, open source is there and it's alive and kicking. So go ahead and play around. Anyway, so let's switch to code. Let's do some coding with FStar. So again, this is the FStar mode in SpaceMax. Play around with it. It is actually, there are multiple ways to set it up. I'm using SpaceMax with Vim mode. And similar to Coq, right? So there is a command in Vim, this is space mn for going to the next command to evaluate. So initially, you would be, your file would look like this. No, okay. Mn. Okay, so initially your file would look like this. Anytime it type checks, you would see this blue bar. blue background that sort of fills up. This is similar to how Coq works, right? And they're sort of trying to fill in the same sort of idea. So this file is called fstar functional, and in fstar you have to name the module with the same name, right? These modules are not as powerful as OCaml modules. They are just for namespacing. They don't give you the abstract types and a lot of the other things that OCaml modules give you. You can ignore this for the moment. Fstar has a particular sort of multiplication which we are using in this file, which you can ignore for the moment. The one nice thing about fstar is that um, very rarely do we actually run fstar code. We end up just type checking fstar code, right? And fstar has this notion of assertions, which we also have in other languages, right? OCaml also has these assertions, but the critical difference between the fstar assertions and OCaml assertions are that these assertions are actually discharged at compile time. So the compiler actually goes ahead and checks that these assertions hold. So what am I doing here? I'm describing a small function, right? The syntax is similar to OCaml. So I'm defining a let max function that takes two integer values. If I1 is greater than I2, then I return I1, else I2. And then I assert that the result of max of 0 and 1 is 1, right? So if you had written the same code in OCaml, you would have to, you can run this program. At runtime, you will get a I mean, the assertion would pass, right? Because this would be true. So the assertion would pass. Here you can get the assertion to pass at compile time, right? So when I compile this program, what is happening underneath is that, as I mentioned earlier, fstar has a SMT solver that sits underneath. And this SMT solver takes the version of the program and then type checks it, ensures that the constraints are actually satisfied, right? It actually goes through the program and sort of encodes them in the SMT language and then goes ahead and type checks it for you. So one thing you will find often is that when the type checking goes through, it's fine. When the type checking fails, the error messages might not be very obvious. This is because of the encoding. You have to take this functional program and then convert it to an SMT language and then feed it down. We will also look at these examples, right? How do you actually debug these and so on? Because part of the course is proof engineering, right? It's not just like proving. I also want you to teach, learn how to engineer proof. So I want to do this. How do I go step by step? Okay, so that was static assertion. This seems like something that you could do in OCaml. What is the point, right? But in fstar, you can write first order logic statements that as part of the assertions. And here is an assertion which reads, for all x, y, z, the maximum, if the maximum of x and y is y and the maximum of y and z is z, right? The maximum of x and z is z. So this is transitivity, right? So x is less than y and y is less than z. So if you compare x and z, you'll get z as a result. So um, so the way I type this for all word is I just type for all as an English word, and then fstar replaces that with the Unicode character, right? So you'll see a lot of Unicode characters. They're all just special things that the editor knows, right? Nothing strange, interesting going on here. If you open this in a text editor, you'll just see for all. But I'm saying something very fundamental here, right? I'm writing down a theorem which states that the maximum function is transitive, right? And if you were to do this in Coq, you would have to do induction on X, right? That is what we'll do. Oh, I'll induct on X. I'll see what the various cases of X are, and then I will sort of go ahead. I'll have to do case analysis here, right? And then I'll get two cases. So I'll have to keep doing this. But these, what we are dealing with here is integer theories. Very simple theories on integers about um, inequalities, right? So we have equality, but also inequalities here. We are dealing with linear arithmetic, and linear arithmetic is a well-known theory that many SMT solvers have. Z3 is the SMT solver that powers fstar, that has very nice support for linear arithmetic. So I don't have to do anything here. The point is, I can just say fstar is this true, right? I have to type space mn, and then that just compiles, right? And what this says is that, okay, that is in fact true, right? So this, if you don't take away anything from this lecture, right, This is the one difference that I want you to take away, which is the benefit of using F star. So the thing that we studied in Cork is that simple programs can be difficult to prove, right? Recall how much trouble we went through for proving the sum of the first n natural numbers is n times n plus 1 divided by 2. That would be very natural here, right? You would still have to do a little bit of work because it involves a loop, but there is very little work compared to all the work that we had to do in Cork, right? Because of the fact that there is an SMT solver that is sitting underneath, right? So that's a beautiful thing that is happening here. Um, I mean, this is completely new, right? So I will. Any questions on this one? Okay, so this might seem very obvious, but a lot of things are happening underneath, right? Let's slowly go through what these things are. Um, for instance, you cannot do this in any mainstream programming language that you have out there, right? That's a fact. So this is something that is incredibly powerful. This is pushing the boundaries of what real programs can do. Why is this useful, right? What do you want to do with this? You can define realistic functions. So here is a factorial function. I don't know why we always go for factorial and Fibonacci, but this is what we tend to do, right? Because we understand these functions easily. We have something interesting to say. So the factorial function here says it's a natural number to a natural number function. So one thing you can do in F star is that you can write down the function just like you do in OCaml, right? But also give it a type, right? Explicitly associating the type that you want to associate with this function, right? So typically we have actually not seen these val definitions in when we study 3100. I believe so. No, actually we saw that. We saw that in as part of the modules, right? So what we are saying here is that, oh, here is the function definition, right? F star will infer the type for it, but I want to give it a more specific type. I'm saying factorial is a natural number to a natural number function, right? And and there are a few things to note here. There are a few things which are so obvious, right? Factorial definition is obvious. If n is less than, if n is equal to 0, then 1. Otherwise, it is n times factorial of n minus 1, right? The other thing is it is using this notation, this mathcal notation for n. The way I type that is I just type nat nat, and that replaces that with a Unicode for n. Okay, so that is obvious. The other thing that is non-obvious is the fact that in Coq, when we try to write this function or a similar function, Coq complained that n minus 1 is not a subterm of n, right? Because Coq was doing syntactic reasoning on the size of the terms. So it saw n minus 1 and it said, okay, n minus 1 is actually bigger. It has like more terms than n, so I'm not going to let it go through. But here, F star actually makes this go through. So F star is not complaining anything here because it is actually using the SMT solver to reason about integer theory. In particular, it knows that n minus 1 is a natural number, and when you subtract 1 from a natural number, um, it is going to be a natural number as well, right? So actually, I'm sorry, it is going to be a natural number that is smaller than the input number. So that is the reason why F star can agree that this function is going to terminate, right? So the termination is really the important bit that I wanted to emphasize here. Um, so yeah. So again, this multiplication is just star. It's formatting that as an X here. When I type a asterisk, it's doing that. Okay. So that's a factorial function. The um, the thing with F star is they're trying to make um, verified functional programming very natural, right? So that is one of the aims of doing this. If it seems obvious, it is by design, right? And stop me if you have questions. Okay, so please stop me if you have questions. And here are the other things that you can do. Obviously, we are in a functional language and we like algebraic data types. So here is the definition of a list type, right? And unlike OCaml, which sort of reverses the polymorphic argument and the actual type name, in OCaml we would write something like this, right? Type alpha. Again, look at this. So I'm typing quote A, and it's rewriting that as alpha. That's just the editor doing the work. So the point is we would write type alpha list in OCaml, and we will define the constructors. But really, if you think about the list as a type constructor, which takes an alpha and then gives you a different type, which is what we had seen in Coq, right? The alpha should really appear on this side rather than before alpha. So it should be here, right? Which is the notation that F star adopts, right? So the only point that I'm trying to make is that the position where the alpha appears is to the right of the name of the type, right? And that's more natural actually. OCaml has got it wrong. So what are we saying here? I'm going to define a type that is a list type, and it takes a parameter which can be any type at all. It takes an alpha type, right? Type is this. It is very similar to the type that we had seen in Coq. A is just some type, right? And there are two constructors. We are using GADT syntax here. So if you use an L, you get a list of A's. If you use cons, you need to provide a head, which is an A, right? And a tail, which is a list of A. And then you get a list of A as a result. I mean, that's the way you construct a list by consing a head element to a tail. The one thing that is perhaps new here is that we actually give names for um, the um, the arguments to the constructor, right? Uh, so we actually name it as head A, right? So the way to read this is that I am naming this as head, and the type is A, and the second argument is I'm just giving it a name as TL tail, and then I'm saying that the type of that is list A, and if you cons a head to a tail, you get a list as a result, right? So this is obvious. So this is different from OCaml. This and this is different from OCaml, but keep that in the back of the mind. We will see why that is useful. Okay, so that's inductive type. We can write recursive functions, right? So we can write recursive functions as we would. So here is a map function that takes a higher order function f that goes from alpha to beta, right? When you see an alpha, it's basically a quote A, and beta is quote B. So it takes a higher order function that goes from alpha to beta, takes a list, right? That is a list of alphas, and it returns a list of beta, right? And it pattern matches the list. If it is null, you return null. If it is cons ht, then you apply the higher order function on the head, right? And you map the rest of the tail of the list, and then you cons the results together, right? This is the natural thing that we would write for um, like the map function, and that just works. We use letrec. We have to use letrec here. And letrec, the syntax is similar to OCaml, so it's trying to stick to OCamlish syntax. So when I'm just compiling it as we go along, okay. And we also have support for lambdas. So here is a map function that maps over this list. So there is a list which has 2 and 1, and I'm writing a higher order function here. And this lambda symbol is just when you write fun, you just get a lambda, right? So this increments the list element by 1, and you get a list which is 3 and 2, but that's not important. The thing that I wanted to emphasize here is the syntax. Of course, you have lambdas as well, which you expect, right? So that also has compiled. Um, yeah, okay. So any questions so far on this? Okay, let's continue in that case. So one thing, the basic construction of the power of F star comes from the fact that we are using what are known as refinement types. They can be viewed as um, a less powerful version of something called as a dependent type. I mean, these two are new terms that we haven't seen earlier. So we will see what they are by looking at simple examples and then building an intuition for what they are. So if you talk to someone, right, and then say, "Oh, what is F star?" The way I would describe it is F star is a language that is sort of OCaml plus refinement types. And what are type refinements? Type refinements are basically constraints that you might add on top of existing types, right? In order to make the constraints more narrower. So here is an example, right? I am defining a type natural number, right? The natural number type is what we had seen a little bit earlier. And the way the natural number type is defined is it says type natural number is an integer type, right? Let's just give it a name. Let's say for any x which is an integer, the natural number type has a constraint. And what is the constraint? X has to be greater than or equal to 0, right? That's the intuitive definition that we would have for um, say, how do you define natural numbers? Natural numbers are also integers, right? They're also integers, and the restriction is that if you only consider the numbers which are greater than or equal to 0, and that is precisely how we write this. And now you can see why we introduce this name, right, on top to the left of the type. So that we introduce this string x here. This could be arbitrary string. If it is x here, you can introduce y, z, or my natural number, whatever. And the only reason to introduce a name for this is that so that we can use that as part of the refinement here. So we are saying that I'm defining a type natural number, which is defined as some x, which is an integer, such that the x is greater than or equal to 0. So that's the way you read it, and that's like valid syntax for that is a valid syntax for F star, right? That is how natural numbers are actually defined. So this is fine, but you are adding very rich semantics here, right? This greater than or equal to 0 is linear arithmetic. If you go back to your um, Coq examples. So we were using these linear arithmetic tactic, and we are trying to manipulate this in very strange ways. So how does this, when you add these things, you have to be sort of, immediately a question should pop up, right? Oh, ML has type inference. So you don't have to write types anywhere. It magically infers the best possible type for a program. But once you add these refinements, the type inference problems become really tricky, right? Because you can have constraints which have complex mathematical properties, and then the constraints might or might not be satisfied. How does this all work out? So it all works out thanks to how um, F star cleverly marries type inference and SMT solvers, right? So let's look at an example to make this more concrete. So you can introduce refinements by adding type annotations. So this is the factorial function that we had just seen earlier, right? This is the same code as what I had in the F star in my Spacemax code, except that I mean it's actually the same code. The way we actually introduce the refinement is that we add a type annotation here, right? We say I could have just written this factorial function with this letrec, this one, and ignored this line. If I had ignored that line, the type that would be inferred for the factorial is integer to integer, as you would in OCaml, right? But I'm saying, okay, I don't want this function to be integer to integer. I want this function to be a natural number to a natural number function, right? And what is a natural number? A natural number is exactly the type that I've defined here. So the proof obligation now is for F star to actually go and check whether this particular definition that you have satisfies this type, right? And what does that concretely mean? If I assume that the input is a natural number, which is what the type here says, I should prove the F star type checker has to prove that the output is also a natural number, right? How does it go about doing that? It goes through the body. Okay, there is a, if n equals 0, there is a condition here. Okay, and there are two cases, and it says, okay, in both of the cases, I have to prove that it is a natural number. Then it looks at the true case, right? In the true case, what does it know? It knows that 1 is a natural number because natural, I mean, that's just by definition, right? 1 is greater than 0, so it's a natural number. Greater than or equal to 0, so it's a natural number. Okay, that's fine. The else case is actually a little bit tricky, right? It has to somehow show that this term is a natural number. So how does that work out? So if you look at this, there are actually many things happening, right? First thing that you have to show is that I have a recursive call to factorial, right? And I need to, what is the type constraint on factorial? The constraint on factorial is that the input has to be a natural number, right? And the first property that the OCaml, sorry, the F-star compiler has to prove is that this recursive call, the argument to this recursive call is also a natural number. It has to prove that n minus 1 is a natural number, right? And that is what I've written down here. What does F-star know, right? F-star knows that it is in the else branch, right? So, and it also knows that n is a natural number. So n is greater than or equal to 0. So that comes from the fact that n is a natural number, right? And it also knows that it is in the else branch. So it knows that n is not equal to 0. And if you sort of combine this, what does it mean, right? N is greater than or equal to 1, right? So I know that n is greater than or equal to 1, and I need to prove, you sort of read this as to show that n minus 1 is also greater than or equal to 0. If n is greater than or equal to 1, then that number minus 1 is always going to be greater than or equal to 0, right? So hence this particular expectation about the constraint on the input of factorial is satisfied. So and then F star says I tick off this. I know that this particular function has the correct argument type. So that's done, and immediately we get a property for free. Essentially, we are doing induction here, right? This is a recursive call on a smaller term. So if I call this function with a natural number, I know by the definition of the type that the result of the factorial is going to be a natural number. I just get that fact for free because that's part of the induction hypothesis. F star is actually doing that for you underneath, right? So now what do I need to prove? I need to prove that this whole term, right, is also a natural number because that is the proof obligation that I have here, right? I need to show, in order to show that this whole term, the term here is a natural number. What are the facts that I know? I know that n is greater than or equal to 0. That's thanks to this constraint on the input. I know that n is not equal to 0 because n happens to be, I mean, we are in the else branch. So n is not equal to 0. I also know, thanks to the induction hypothesis, that the result of calling factorial on n minus 1 is also a natural number, right? That fact is also there. Now, with all those facts, I need to show that n times that term is greater than or equal to 0, which is natural number. So here we are using the property that if you take a natural number and multiply that with another natural number, you get a natural number as a result. This is part of the integer theories, right? So, and that is the reason why this function actually type checks, right? And this proof obligation is actually discharged to the SMT solver underneath, and then the SMT solver says, okay, I can actually show that assuming these facts, this fact is true. And if SMT solver comes back and says, okay, it is fine, then F star says, I accept this function, right? Even though it seemed very natural, F star is actually doing all this work for you underneath, right? So that is these are the steps by which F star is actually proving that factorial can be assigned the type nat or a nut. Any questions on this? So the point to take away is that F star is doing a lot of work underneath, right? Even though it seems like it is not doing anything at all. Okay, so okay, so if there are no questions, let's keep going, right? So of course you can review the lecture and ask questions later. but I'll just keep going. So one way to think about refinement is you have a type, right? And the refinement is sort of adding constraints and making it narrower. So that is done by type annotations, right? But we can also pretend that a narrow type is wider, right? I can always say if I get a natural number, I can pretend that this natural number is an integer. That is also useful, right? Because if I have a function which expects an integer and I give you a natural number, of course you can call that function with that natural number because every natural number is also an integer. So the other question is by we can refine types by adding type annotations. We can also widen it, and the way you widen it is this way. Um, yeah, so this so you can eliminate refinements by subtyping. So we have this notion called subtypes because we have this rich notion of refinements where we sort of narrow and widen the types, right? Um, we have this natural hierarchy of types. We can start very simple here. So we call that a natural number type is a subtype. So this is the syntax that we use for subtyping of integer. What does that mean? Every natural number is also an integer. Is precisely what we are claiming. Okay, so that's the thing that we are claiming. You can sort of also look at it as an implication this way, right? If you have a natural number, then it implies that it is also an integer, right? So why is this useful? So here is one example, right? I can always say this factorial function is the same function as I described here. So it's a natural number to natural number. So factorial of 42 returns the factorial result of 42. That is going to be a natural number, but I can always give it a type which is wider. So it's a super type of nat, right? So because of this subtyping relation here, I can pretend that the value that I get is an integer because natural number is a subtype of integer, right? I'm just claiming that I get a something which is narrow, and I'm pretending that it's actually part of a wider type, which is true thanks to this subtyping relation. And similarly, we have a subtyping relation for functions because we are in functional programming world. We also have to think about what is the subtyping relation for function. So subtyping relation for function is sort of um, not natural. Okay, so let me put it that way. So it might seem surprising at the first moment, but it's actually very standard. Okay, um, so with that, let's just look at what the type that I prescribe here. So I take this factorial function, which is a natural number to a natural number function. This is agreed upon, right? We know that it's a natural number to natural number function. I actually give it a different type annotation. I say that let me define this function f, which is the same function as factorial, but I'm just refining the type so that it will only accept inputs which are greater than 0 and return outputs which are integers. I mean, why is this correct, right? If you sort of think about this factorial function accepts natural numbers, right? It accepts anything which is greater than or equal to 0. I am actually constraining the input type and saying that I'm going to pretend as if this function is only going to accept values which are greater than or equal to 1, right? So this is greater than 0. So if you think about this as a tube, I'm saying the tube has say 10 centimeter diameter. I'm saying, okay, I will pretend that this tube only has 5 centimeter diameter. So I'm going to sort of, this will still allow anything that is smaller than or equal to 5 centimeter diameter. I'm just going to pretend that this is going to accept smaller inputs, right? Right. But on the other end, I'm actually claiming it is producing an integer, right? Why is this naturally, right? Intuitively, why is this right? We know that the factorial function is going to return a natural number, and every natural number is also an integer, right? So I can pretend as if this function is returning an integer. Of course, in reality, it will only return natural numbers, but we don't lose. I mean, it's absolutely correct that it also returns an integer. thanks to this subtyping relation, right? So if you sort of look at it more in abstract terms, not in this concrete example, but in an abstract term, we can claim that this function a arrow b is a subtype of a prime arrow b prime, right? If b is a subtype of b prime, but on the argument side, it is actually flipped. A prime is a subtype of A. So this is what I meant by looking a little bit strange, right? Observe that here we have B subtype of B prime, but A prime subtype of A. The way to reconcile this is just look at this example, right? Here we are able to give this type annotation because um, this type that we actually prescribed for this factorial function, right, is actually a super type of nat or a nat. That is why we are able to prescribe that. Similar to how we prescribed integers for a natural number type. So I want to show that the type annotation that I've given here, right, is actually a super type of nat or a nat. And the rule here says that you need to have two conditions, right? Nat has to be a subtype of integer. B has to be a subtype of B prime. Nat has to be a subtype of integer. That is true. Every natural number is an integer. But for the argument, you flip it around, right? You actually have to show that this type, which is any number that is greater than or equal to 1, which is greater than 0, is a subtype of natural number. It is true because if a number is greater than or if a number is greater than 0, then it is greater than or equal to 0, right? And hence this particular subtyping relation holds, and hence f star is able to give us prove that this particular implementation is correct. So the only thing that I want to remember from this function subtyping is that these arrows are the subtyping relation is sort of reversed. There is a lot of if you sort of take away this intuition for now and sort of relate this with this example, you'll be golden, right? I don't want you to think about anything else for now. We won't do this function subtyping explicitly. It naturally works out most of the time, right? You wouldn't have to deal with it all the time explicitly, but bear in mind that this is what the subtyping relationship for a function is. That the argument types are actually in the reverse order, right? And that is the perfectly intuitive way in which we have to look at subtyping for functions. Questions on this? I was very stumped when I.
Uh,
Yeah, go ahead, Deepali.
Sir, if instead of int in a function, if I
Hmm.
use nat x greater than or equal to one,
Yeah.
then according to the definition, it is wrong. Means it is not the subtyping, but actually it is the correct definition of the
So
factorial.
where is it? So you're going to use. You're
No,
saying
not in f. Instead of
here.
int here, yeah.
Okay.
If instead of int,
Sorry.
if I use nat,
Instead of this particular
yeah.
position, you're
Yes.
saying.
Yes.
Okay. So instead of integer, what do you want to say?
If I use nat x greater than or equal to 1.
Okay, let's try that, right? So let me switch to code, and then let's try that. We actually have an editor in the background, so why don't we use that? Um, so just to show that these things work, right? So here is the factorial definition that has a integer, so that works. Here is the int here, that also works. So what you're saying is I want to define something else here, right? So let's call it f prime. Instead of integer in this position, what do you want to do, Deepali?
N means nat x greater than or equal to 1.
X greater than or equal to 1. Is this correct?
Yes.
Okay. So what do you think will happen here? Any guesses from people?
Means according to the definition, it is not following the subtyping.
No. Why is it not following the subtyping?
Because can you move back to that?
Yeah. Okay. So let's do this, right? So the subtyping is failing, right? So the subtyping fails, right? As it should. Um, oops, I've gone much further than where I should be. Okay. But here we would have NAT is a subtype of um, y greater than or equal to 1, right? That is what we'll have. Deepali?
Yes. But
But that,
according to the definition of factorial, it is correct. Means output should be always greater than or equal to 1.
oh, okay. You're asking that. Okay. So the point is a really good question. So the point is, um, so really good question, Deepali. This one is because the specification that we give for factorial, right, is based on what the type is inferred and how the um, type is assigned. What is the refinement that we actually give? You can, of course, give a very specific type, as we will see. In fact, if you can actually write down the type in smaller ways, right, where you can sort of say this particular function has a specification that is precisely describing what factorial does, then f star will be able to prove that this is true. But what information does it have currently, right? If you just think about that question, the only information that it has is that factorial is a NAT or a NAT. It doesn't know anything about the implementation of factorial. It only knows about the types of the functions. So it's not going ahead and looking into what the factorial definition is. And that is why it is not able to prove that this is true. And hence it doesn't type check. Does it sort of make sense, Deepali?
Yes, sir.
If you just keep this in mind, right, when you are doing type checking, you are not actually looking. But so we are in a world where we have higher order functions, right? And if I say map takes this function, it's a really beautiful question actually. If a map takes this function, higher order function f, and the only constraint that I actually specify for this higher order function is that it's an alpha to beta, right? The F star system, the compiler, the type inference, the type checking can only know that f is a function from alpha to beta. It might be the case that f is actually a function from alpha to alpha, but without looking at the actual definition of f, it cannot know what it is, right? And here in this statement, right, the way we actually type check this is we just have a type for this uh, factorial variable. And the type that we have is NAT or a NAT. We don't know anything about how the factorial is defined. The only thing the type checking procedure knows is that it's a NAT or a NAT. And hence the failure of this condition, right? So if you actually had a system which fully knows about everything, which is not possible at all, you cannot go ahead and write this function, right? You cannot. If you always wanted to design a system where you knew the full implementation of every higher order argument, say I need to know every instance of f here, then it wouldn't just work. The type checking wouldn't scale. So the reason why this proof fails is that f star doesn't even know. The only thing it knows about factorial is that it's a NAT or a NAT. Really good question, but does that answer your question?
Yes, sir. Yes.
Okay. Good question. Good question,
Means
Deepali.
we always have to means whatever it is greater than that, we can always infer that.
Yeah. If you have a true fact, then you can actually specify that as part of the refinement. You can give precise specifications. Actually, I'll cover that in the. It's a really nice segue into what I want to cover next. But I'll just go through the steps. Anyway, this doesn't type check, and when it doesn't type check, F star says subtyping check failed. Right? It says that it says I expected a type which is x not greater than or equal to 0, right? It is expecting this type, and that is what it is complaining, right? But got type not, right? Ignore the start for the moment, but F star can only give you this much information on failure. It cannot precisely point out counterexamples. Because the way F star type checker works is a combination of the usual type checking rules for functional programming plus SMT solvers. So as you will see, sometimes what happens is that it will just say SMT solver could not prove the query, right? And then it will just give up. It won't give you precise reasoning for why the thing failed. And that is one of the downsides of proof engineering with the rich types. I mean, this is active area of research, but we will hit these roadblocks, and this is one roadblock that we've just seen. Right? We know this type is wrong, but we don't know why. I mean, we have to manually reason about why this is wrong. Anyway, so moving ahead, right? Um, so we know that factorial function is a nat or a nat. If I move my mouse over it, it tells me that it's a nat to nat function. Ignore this dot for the moment. I'll come back to that. It's a nat or a nat. So if I apply 0, it type checks, right? But f, I've given the type as x is greater than 0, right? So if I call f on 0, even though it's the same factorial function, its type is actually more constrained. It's a subtype, right? So this will complain here. So I expected a type which is natural number greater than 0, but you gave me a 0. I got a type int, and all it's saying is that you it is giving the inferred type here, but the way you should read it is that the constraint on the input is that oops, it's going away. The constraint on the input is that it has to be greater than 0, but you gave me a 0 which doesn't satisfy the constraint. So I'm not going to make this go through. Right? So F star is able to do this statically. Okay, so that was that one. So just to give you the question that the answer to the question that Deepali asked, right? There is actually the type that we are giving for factorial is sort of one possible type that we can give for factorial, right? So here is an increment function. Let's just look at the function first. The increment function says it takes an x and it just returns x plus 1, right? One possible type that you can give for this increment function is it takes an integer, which is an x, and it returns a y, right, which is also an integer. And the constraint on this return value is that y is greater than x, right? This particular type of definition is known as a dependent type. It is also a refinement type, but it is known as a dependent type. Uh, and what is the meaning of this term dependent? The type here, right? The type that is here is actually dependent on the value, right? For the input. So X is being actually used in the type. So whatever X is, that value influences what this type is, right? And that is known as dependent types. We will use dependent types as well. We are actually saying the constraint on the output is actually based on the value of the actual input, right? The constraint for the output type is actually referring to the variables here. So if we call it a dependent type, so that's the first thing that I wanted to express here. The second type that I want to say is that this is just one specification that you can give for this particular function. Of course, it is true that the output y is greater than x, right? But there are many specifications that you can give. So let's first convince ourselves that this is true. If you give a wrong type, this won't go through. So I give a type which says increment function, which I call increment 2, where the output is less than x. This is not true, right? So if I compile it, subtyping check will fail. So it is expecting a type where y is less than x, but you are actually adding 1 to x. Then the constraint is not satisfied, so this won't go through, right? Unlike OCaml, right, where there is one one best type for any function. We can have many types for the same function. So this is one correct type, right? This y greater than x is one correct type. You can also say y is greater than or equal to x, right? That is also correct. I'm not saying anything wrong. I'm just saying that this increment function here is going to return a value which is greater than or equal to the input value. That is also true, right? I can give it a, oops, that is also true. That is increment 3. I can give it a even more imprecise type. I can give it, say, it takes an integer, returns an integer. This is also true. This is the type that we will have in OCaml, right? I can be even more specific. I can only say that this increment function takes an x, which is a 5, which is exactly equal to the number 5, and returns an output which is exactly equal to the number 6, right? And this is also true, right? I mean, this may not be useful, but this is also true. This also type checks, right? All of these types, right? This increment 1, increment 3, increment 4, increment 5 are all sort of valid types. So what is the relationship between all these types, right? And the relationship is that they all belong to one family, right? They all belong to this family. Let's call this family T, such that there exists a type T prime. There exists a most precise type T prime, which is the subtype of all these types. All these types are sort of under specifications of what is actually happening in this increment function, right? This is precisely what Deepali asked, right? For factorial, we actually said it's a natural number to a natural number, but actually we are not fully capturing the specification. It's not a full functional specification of what the factorial function does. We just said it's a natural number to natural number. So what is this most precise type? So the most precise type is this, right? For increment function, we can say that x takes some integer, right? And it returns some integer y, where the output y is exactly x plus 1, right? It is exactly x plus 1 because that is what it is doing, right? And in fact, this particular type is in fact the subtype of all of these types. You can work it out with the subtyping rule that we had, right? So what we've done is we've captured the full specification of what increment does in this type, right? Um, and often what we try to do is to, so you can sort of think about, so the key takeaway is that when we look at types, right, they're sort of, they define a spectrum of the possibilities in these rich type systems. You can be less precise and be correct, or be more precise, or be absolutely precise and be correct as well. For increment function, this is the absolutely precise type that you can give that is correct, but all of these are also right, right? So there is actually a spectrum of these types. And for factorial, we gave one possible type, which is a correct type, but that is not a full functional specification of what factorial function is doing. And that is why F star was not able to actually prove that the type subtyping rule actually went through. So yeah, so I'll stop here. I think this is a good point to stop. Any questions on this? So what you will see is that oftentimes we don't want to give the full functional specification, and we can't actually give full functional specifications of every function. If you write a really complicated function, sometimes the summary of the effect is what you want to capture. We will see a lot of that later. One example is, let's say I append two lists. The property that I want to capture may be just saying the length of the appended list is the length of sum of the length of the individual list. I don't actually want to say anything more. I don't want to say that the order of the element in the first list is preserved, the order of the element in the second list is preserved, the list of elements that appear in the second list appear after the first list. All of these are like true about the append function, but the property that you might want to prove might not involve the complete full functional specification of what is required, right? So sometimes the proof engineering is essentially you have a specification in mind and you have an implementation, and it's about the balance of what you want to prove and what you actually have done in the implementation, and how do you marry this. And here is an example of that in practice. Anyway, we'll see more of this in the subsequent classes. I'll stop here. Thank you very much, and see you tomorrow. Bye bye.